Hello and welcome. In this video, we'll walk you through the configuration flow for AMD Spartan UltraScale Plus devices. We'll cover the configuration process, give an overview of the programmable device image, PDI, and its generation, and explain debugging techniques along with pre- and post-configuration security features. To begin, let's explore the configuration process for AMD Spartan UltraScale Plus FPGAs, covering the fundamentals and overview, the three key phases of configuration, and the supported interfaces. FPGA configuration is the fundamental process of defining an FPGA's functionality by loading application-specific data, such as a bitstream or programmable device image, PDI, into its volatile internal memory. This essential step occurs after power-up, necessitating data storage in non-volatile memory like flash. AMD FPGAs are highly flexible, allowing multiple in-system reprogramming iterations via serial or parallel data paths, including the industry standard IEEE Standard 1149.1 JTAG boundary scan interface. This flexibility accommodates diverse application needs, supports configurations using full or partial bit streams, and enables these configurations either automatically from external memory or via an external device like a microprocessor. AMD Spartan UltraScale Plus FPGAs feature advanced configuration logic built around a dedicated platform management controller, PMC, which plays a central role in managing device boot, configuration, and security. These Spartan UltraScale Plus devices use a modern configuration format called the Programmable Device Image PDI, replacing the traditional bitstream used in earlier FPGA families. The configuration process begins after power-up, when the PMC's configuration controller runs the boot-ROM firmware to initiate the device configuration process by loading the PDI through special configuration pins, which serve as the interface for various configuration modes. The introduction of the PMC in AMD Spartan UltraScale Plus devices marks a significant evolution in FPGA configuration. The PMC acts as a secure configuration engine that orchestrates the entire power-up sequence, loads the PDI, and manages critical security functions such as authentication and decryption. Its architecture includes a configuration controller, I/O interfaces, a security engine, and a configuration control unit. After power-up, the configuration controller runs the boot-ROM firmware and the platform loader manager to configure the device. The boot-ROM's responsibilities include reading the configuration mode and setting up registers for the selected mode. It also searches for a signature in the programmable device image boot header to verify valid configuration mode, connectivity, before loading and initiating the Platform Loader Manager PLM. This PLM performs boot and configuration of the Spartan UltraScale Plus device, and then continuously provides services after the initial boot and configuration. The PLM then handles user-defined settings, loads the PDI securely or non-securely, and supports full or partial reconfiguration. This integration simplifies dynamic reconfiguration, enables comprehensive system health monitoring, and provides integrated power domain control, ultimately ensuring enhanced reliability, security, and flexibility for advanced applications. The configuration process in AMD Spartan UltraScale Plus devices, orchestrated by the PMC, follows a streamlined three-phase sequence that's consistent across all configuration modes. Phase 1. PMC hardware. Power up and reset. This initial phase is handled by the PMC hardware itself. When the device receives valid power, the PMC detects it and then releases the program B-pin, which initiates the configuration sequence. During this time, the configuration hardware samples the mode selection pins like M2 to 0, clears internal system registers, and performs crucial cryptographic hash checks to ensure the integrity of the configuration process. This ensures a clean and secure start. Phase 2. Boot ROM, initialization and platform loader and manager. Following Phase 1, the device's boot ROM takes over. It begins by performing basic integrity checks on the incoming PDI and reading the device's mode register. A key task in this phase is to search for a specific identification signature within the PDI. Once a valid signature and checksum are found, the boot ROM proceeds to load the Platform Loader and Manager (PLM), a crucial piece of firmware, into the PMC's internal RAM. For master configuration modes, if the initial signature isn't found, the boot ROM can even execute a fallback mechanism, searching a next 32 kilobyte address for a valid image. Phase 3, Platform Loader and Manager PL, Image Processing and Configuration. In the final phase, the PLM takes full control. Its primary responsibility is to complete the entire PDI image processing and loading from the chosen configuration source. This involves configuring various registers based on the selected mode and user settings. The PLM handles both full and partial PDI configurations, ensuring that the programmable logic PL fully starts up. Once the configuration is successfully loaded and the PL is operational, the device asserts the Done pin, signaling that it is ready for the user application. In AMD Spartan UltraScale Plus FPGAs, the configuration interface is selected using the mode pins, specifically M2 to 0, M0, M1, and M2. These pins determine which configuration method the device will use after power-up. During the initial power-up sequence, phase 1 of the configuration flow, the PMC samples the M2 to 0 pins to determine the configuration mode. These pins must be held at a constant DC voltage, either pulled up down or tied directly to ground VCCO 0, and their values must be stable before the program B pin, which initiates the configuration process upon deassertion, is deasserted. The selected mode is captured at power-up and maintained throughout device initialization, while init B is low. The combination of logic levels on M2 to 0 selects one of the following configuration interfaces. JTAG. This mode allows for direct programming and debugging of the FPGA via a JTAG cable connected to a host system. It's commonly used during development for quick iterations and debugging. Master SPI. In this mode, the FPGA configures itself autonomously from an external SPI nor flash memory. The device acts as the master, clocking out data to read its configuration image. Master OSPI. Similar to Master SPI, this mode enables the FPGA to self-configure from an octal SPI flash. It uses an 8-bit data bus for significantly faster configuration times compared to standard SPI. Slave Select Map. This parallel mode allows an external processor or controller to configure the FPGA. It supports 8-bit, 16-bit, or 32-bit wide data buses, offering high-performance configuration controlled by an external source. Slave Serial. In this mode, an external source configures the FPGA by sending data serially, 1 bit at a time. It requires dedicated control signals from the host to manage the data transfer. Choosing the optimal configuration mode is important for efficient system design. Configuration modes can affect pin allocation, I/O bank voltage requirements, and system costs. Recommended design flow and configuration factors include the following. Determine the optimal configuration mode early in the design cycle based on system characteristics. Utilize JTAG as an additional mode for debugging purposes. Plan for multifunction pins used during configuration to prevent conflicts with other uses. Ensure quality signal integrity for key signals, such as the configuration clock, during PCB layout. Consider all aspects of the configuration sequence to reduce configuration time, including power-up time. Generate the configuration PDI using the latest AMD tools, targeting the correct device version. The configuration process in AMD UltraScale, UltraScale Plus FPGAs, and Spartan UltraScale Plus devices differ significantly, primarily due to the introduction of the Platform Management Controller (PMC) in the latter. In UltraScale, UltraScale Plus devices, configuration is handled by a dedicated configuration engine circuitry and the internal configuration access port (ICAP). These devices support standard configuration modes such as JTAG, master-slave serial, master-slave select map, and PCIe-based configuration in some variants. The bit stream is loaded directly into the FPGA fabric without the need for an embedded processor, making the configuration process relatively straightforward and monolithic. In contrast, Spartan UltraScale Plus devices adopt a more advanced, processor-centric approach by incorporating a PMC. The PMC is responsible for managing the entire boot and configuration process, including security features. The configuration process is multi-stage. The PMC first boots from a non-volatile memory source, such as QSPI, eMMC, or SD, then authenticates and loads the PDI into the programmable logic PL. This architecture supports secure boot and partial reconfiguration natively and integrates seamlessly with the AMD boot and configuration framework tools. In UltraScale Plus devices, the boot ROM falls back to the golden image located at address 0 if the update image at a higher address is found to be corrupted. In Spartan UltraScale Plus devices, the boot ROM initiates a fallback if a valid PDI boot header signature is not detected at address 0. If no valid boot header is found at this location, the boot ROM automatically increments the address by 32 kilobytes and continues searching for a valid signature. Security-wise, UltraScale Plus devices offer optional encryption and authentication, which often require manual implementation or external control. Spartan UltraScale Plus devices, however, include built-in secure boot capabilities, hardware root of trust, and automated PDI validation through the PMC. Reconfiguration in UltraScale Plus FPGAs is typically done via ICAP, whereas for AMD Zynq adaptive SoCs, Processor Configuration Access Port PCAP is used. Both these ports may require manual setup. Spartan UltraScale Plus FPGAs simplify this with PMC managed dynamic reconfiguration, power domain control, and system health monitoring, making them more suitable for modern, secure, and flexible applications. Next, let's dive into the Programmable Device Image, PDI, exploring its role, format, and how it's generated for AMD Spartan UltraScale Plus FPGAs. The Programmable Device Image, PDI, is a modern configuration format introduced in newer AMD FPGA families like Spartan UltraScale Plus and Versal devices. It replaces the traditional bitstream used in earlier devices such as UltraScale and UltraScale Plus devices. Unlike the monolithic bitstream, which is a flat binary file containing only configuration data for the programmable logic, the PDI is a containerized format. It can include multiple partitions such as configuration data firmware, metadata, and crucial security headers. One of the key distinctions is in their processing. The bit stream is directly loaded into the FPGA configuration logic, typically via interfaces like JTAG or SelectMap, and does not inherently support advanced boot or security features. In contrast, the PDI is processed by the Platform Management Controller, PMC. The PMC manages a sophisticated multi-phase boot process, including validation, decryption, and fallback mechanisms, making the PDI format inherently more robust, secure, and flexible. AMD Spartan UltraScale Plus FPGAs specifically utilize this proprietary PDI file format for booting and configuration. The PDI typically includes boot header, essential for initial processing, Platform Loader and Manager, PLM, the .L firmware responsible for managing the boot process, Programmable Logic, PL configuration data, the .rcdo file, which is the equivalent of the bitstream data. The maximum size for a device's PDI image can be affected by generation options like compression. It's important to reserve memory space for the full uncompressed PDI size, as compressed images can vary in size between design iterations. Additionally, security features can impact the overall image size. Because configuration data is stored off chip, there's a possibility of unauthorized duplication or modification. To protect the PDI, and any embedded intellectual property, advanced security techniques are employed. PDI authentication verifies the authenticity and integrity of the PDI, while encrypting the configuration data using an AES-256. Key protects against unauthorized access. The PDI file format is loaded by the Platform Management Controller into the AMD Spartan UltraScale plus FPGA. The PDI supports both non-secure and secure variants. A non-secure PDI is simpler and suitable for development or environments with less stringent security requirements and contains a boot header, PLM.ELF, programmable logic, PL data bitstream equivalent is the .rcdo, and hash block for integrity checking. In addition to the above components, a secure PDI image comes with an option to include cryptographic authentication and optional decryption. This ensures that only trusted and untampered images are loaded into the device, which is critical for high assurance applications in defense, automotive, or industrial systems. A secure PDI can also contain additional physically unclonable function, PUF helper data, and public keys, SPK or PPK. The PUF helper data is stored in an additional PDI and is unique per device. Generating a PDI for AMD Spartan UltraScale Plus devices requires the standalone BootGen command line tool, part of AMD Vivado Design Suite, as direct tickle commands for PDI generation aren't used. In Vivado project mode, in GUI mode, click Generate Device Image in the Flow Navigator to generate a complete PDI in the runs directory. In tickle mode, execute the command launch runs dash to step, write bitstream to launch the run up to the PDI generation step, which also produces a complete PDI in the runs directory. In Vivado non-project mode, with the implemented design checkpoint open, run the write bitstream tickle command. This will generate the bitstream.bit, boot image format.bif, and any additional files required as input for the BootGen tool to create a complete PDI, all in the working directory. Then, in a new terminal window within the same directory as the .bif file, run the following command using the correct .bif file name generated by the Vivado tool and your desired PDI name. Finally, let's look at debugging and security in AMD Spartan UltraScale Plus FPGAs, covering error aggregation, configuration debugging techniques, and pre- and post-configuration security features. The AMD Spartan UltraScale Plus has an error aggregation module, EAM, that aggregates the errors specified and allows the users to respond to specified error conditions. The EAM has 3 responses for handling the non-masked aggregated errors: assert init B pin low, issue a system reset SRST, or issue an interrupt that enters the secure lockdown SLD state, depending on the severity. The PLM allows for one option response on each error specified. These example error conditions that can cause an EAM response include timeout error, AXI error, SBI overflow error, eFuse error, voltage supply error, temperature error, PMC ECC error, PL error, JTAG toggle error, tamper error. The boot ROM and PLM error codes and the response to it can be found in the AMD Spartan UltraScale Plus FPGA Configuration User Guide UG860. Effective debugging during configuration is essential to identify and resolve issues quickly. AMD provides several tools and techniques, including physical status pins, JTAG registers, and basic validation checks, to streamline the debugging process. PDI options verification. Ensure PDI properties and flash programming options are correctly implemented for the chosen configuration mode. Use report property all current design to verify PDI options, and always review correct all DRC warnings from PDI generation. Physical status pins. Monitor accessible board pins like init-B for initialization completion or CRC errors, and done for successful configuration. JTAG registers access key AMD Spartan UltraScale plus FPGA JTAG registers, including ID code, JTAG status, error status, and firmware status, for valuable debug data. Basic checks. During configuration, perform these checks to isolate issues. Verify the PDI format includes the correct XLNX signature in the boot header. Attempt configuration using an alternate mode, example JTAG, or a known good PDI image. Try a slower configuration clock frequency if encountering issues at higher speeds. Reduce the number of non-default configuration PDI options. Verify proper data reception at the destination device and ensure the latest AMD tools are being used. Security is a continually evolving field, but there are a few key ways to minimize your exposure. Generally, the customers care about three main areas: protecting IP, preventing tampering, and maximizing device uptime. Protect PQC with NIST-approved algorithms, keep our technology safe as quantum computing keeps evolving. AES GCM for speedy and secure configuration, PUF for unique device identification. Tampering, customizable tamper responses by implementing permanent penalty to protect the device's security features against any misuse. Maximize uptime, enhanced SEU performance, for example medical applications where reliability is important. Here you can see how AMD has improved pre-configuration security features across Spartan 6-7 series, UltraScale Plus, and the latest Spartan UltraScale Plus FPGAs. The Spartan UltraScale Plus device includes encryption using AES 256 in GCM mode. It supports both symmetric and public key authentication, making sure only trusted users can access or configure the device. It also adds a root of trust with replay protection and anti-rollback features, which prevent older or unauthorized versions from being used. Like earlier devices, it blocks readback to stop anyone from copying the design, but it goes further with protection against power analysis attacks and secure key loading. The Spartan UltraScale Plus device is also ready for the future, with support for post-quantum cryptography, PQC, and private public key cryptography. The post-quantum cryptography, PQC, is essentially designed to safeguard our devices from potential threats by quantum computers. It's like having a security system that's ready to protect against tomorrow's threats. The private public key cryptography is like having a custom key for a lock. Only the correct key, the public key, can unlock the data encrypted by the corresponding private key. It ensures a secure process when making changes to the FPGA, allowing only valid configurations to be implemented. Overall, Spartan UltraScale Plus devices offer a much stronger set of built-in security features, helping protect your system right from the start. Post-configuration security plays a key role in maintaining the integrity and reliability of the FPGA system. The table highlights how AMD has strengthened post-configuration security across generations, with the AMD Spartan UltraScale Plus FPGA offering the most comprehensive set of features. Post-configuration security features include checks for single-event upsets, which help detect and recover from unexpected changes caused by radiation or other external factors. JTAG interfaces can be disabled or monitored to prevent unauthorized access during debugging. Each device has multiple unique identifiers, like device DNA, user programmable eFuse, and PUF, making every FPGA traceable and tamper-aware. On-chip monitors track temperature and voltage conditions, and the Program B intercept prevents unwanted resets during operation. Tamper events are logged, and features like permanent JTAG disable, decryptor disable, and tamper penalties add extra layers of irreversible protection if tampering is detected. A permanent tamper penalty protects the FPGA from unauthorized changes. If someone tries to interfere with it, our system locks them out. This means your device's settings stay secure, just as you left them. The Spartan UltraScale Plus FPGA also includes a physical unclonable function for secure key storage and a true random number generator to support strong cryptographic operations. The physical unclonable function, PUF, gives each of our FPGAs a unique identity, like a fingerprint. This helps to ensure that you're working with a genuine device, not a clone or counterfeit. The True Random Number Generator, TRNG, creates totally random numbers, which are needed for encryption. This keeps the data in your device safe and secure. Altogether, these features make Spartan UltraScale Plus FPGAs highly secure, even after configuration, ensuring system integrity throughout their operational lifecycle. To summarize, AMD Spartan UltraScale plus FPGAs feature a modern configuration architecture built around the Platform Management Controller, PMC, and the Programmable Device Image, PDI. The PDI is a comprehensive programming file that offers enhanced security and supports multiple configuration modes like JTAG, SPI, and SelectMap. The device configuration follows a distinct three-phase sequence, which is managed by the PMC's boot ROM and the Platform Loader Manager, PLM. For detailed guidance, refer to the Spartan UltraScale Plus FPGA's Configuration User Guide, UG860.